Okay, why don't we begin here? So today you had two subsections you needed to examine. The first one dealt with model building again. It's the part two of a two-part set of subsections on model building. And for this particular case, we looked at data that was simulated from an SARIMA 111 model. And we wanted to try to find the best model for it. And so since we know what the true model is, it gives us, I guess, another example of how, let's say, Monte Carlo simulation can help, it can be used as a learning tool. So we want to see, will this model building process actually conclude with the correct model? And there was a lot of justification for using an SARIMA 111 model in the end, but there was also some justification for using a different model, an SARIMA 211. And so it will be interesting to see then, well, this is what wasn't in the notes, is there much of a practical difference in the end for these two different models? The correct model versus the one that was actually incorrect, but that potentially could be chosen. And so what I decided to do was, well, let's take a look at the forecasts for both of the models. And so if we take a look at, for example, for one time period into the future, actually, let's look at the forecasts first. The forecast is negative 486.36 for the SARIMA 111. And then take a look at this for the SARIMA 211. It's negative 486.4539. So really not much of a practical difference. And if we take a look at then the corresponding confidence intervals, they are also pretty close. But what about 5 time points into the future? Well, we start seeing some differences between the two. And depending upon the context of, let's say, an actual application, this may or may not be important. Without having any context, you think, well, that probably isn't too important. But it still depends upon the application. And we can see that the confidence intervals are getting a little bit farther apart in terms of what at least the upper bound says. But relatively speaking, they're very similar. So even though we did conclude, we said that a different possible model, a different model was possible, the practical difference most likely would be very small in this particular case. So also in the notes, we took a closer look at the examine.mod function, which I introduced last Tuesday. And the purpose of this is just to make your life easier. Well, I guess there's multiple purposes. One, to make your life easier to do all these diagnostic plots. But second, also shows you how, again, you can extend the capabilities of R to satisfy your own needs through writing your own functions. And I think that at the end of the notes, there's a nice little summary. This is of the model building process. This would be a great place to study from. Now, the second subset of notes talked about SARIMA models. The S stands for seasonal. So now we have data that's collected, let's say, over months. And maybe the January, let's say, 2024 value is going to be maybe highly correlated with the January 2023 value, again, due to the nature of the actual application. And so we have seasonal data. It could be quarterly data. It could be weekly data. There's other interpretations of what seasonal could be. In fact, you will have a unique one coming up in the next subsection of the notes where we talk about university enrollment data. And so this is what an SARIMA or a SARIMA model looks like. We say, in terms of symbols, we say SARIMA PDQ. This is our regular non-seasonal aspect of our model. And then by, or the multiply sign, a capital P, capital D, capital Q, which gives us the order now for the seasonal part, where the number of time points for a season is at little s. So if we had monthly data, S would most likely be 12. If we had weekly data, 7. And so then when we start writing out the model, here are the seasonal aspects. And so it looks just like a regular old SARIMA model, what we've done before, but now everything corresponds to this season S. So instead of having, let's say, 1 minus phi 1 times b, now we have 1 minus phi 1 times b to the s power in that AR operator. Notice also how we are using capital letters, capital Greek letters now. These are going to be, the actual phi 1, phi 2, and so on are actual parameters that we want to estimate. Then we also have just the regular non-seasonal aspect to our model as well. Okay? Now, you can see that this model gets complicated. In fact, I even showed in the notes that, well, I could even have additional AR or MA operators as well with these kinds of models. Rarely, if ever, do you actually see that in practice, but it is possible. We will just simply focus on this here. Okay. Now, in order to choose particular models, once we have the seasonal aspect, we basically interpret the ACF and PACF just like what we did with the non-seasonal. But now we focus on lags corresponding to S. 2 times S, 3 times S, to try to interpret the seasonal aspect of a model. We can then continue to work with the SARIMA function when we estimate these models. There's a seasonal argument that comes about with that. And so overall, it's just a nice little extension. And we'll have one more subsection on seasonal models next time. Are there any questions, though, regarding the end of the model building and the beginning of the seasonal part? Okay. Now, last time we talked about some radon data that was actually collected in my house. And after class, I realized, well, I never told you, well, what actually happened in my house. Basically found out that we did have a radon problem. And so what we actually did, just in case you're curious, we installed a fan system. This is the typical way that this is handled. Basically, a pipe was basically inserted in we have what's called a sump pump pit in our house, which is common in this area of the country, that in case there ever got to be water in your basement, this pit can be used to help drain the water. And so anyway, so this radon mitigation company came and capped that hole in our basement, put a pipe in it. This pipe then extended all the way up to the top of the house and went through the roof. And a fan was installed in the attic that basically sucks air out from underneath our basement to get rid of the radon. And so we had an actual test that was done after this was installed. And we have very, very, very low readings of radon now in our basement. So something, though, that might be of interest to think about. Unfortunately, I had that open and somehow I closed it. So here's the actual data that was collected. I'll make this a little bit bigger. Take a look at this. Let's see here. So at 7 a.m. and 8 a.m. on one particular day, we had some low readings relative to what you see around it. 7 a.m., 8 a.m. The next day, we have some low readings around it as well. And you can keep on going through the data set and see something similar. All about that same time of the day. Any thoughts about why that might be happening? Well, maybe we back up a second here. So if we see something like that happening, maybe we have seasonal data. Because after all, we are collecting stuff through time, hourly time. And it seems like about the same time each day, we're having something similar happen. That would mean that we have some kind of autocorrelation. Since we have hourly data, the season would be 24. Any thoughts about why this would happen at this time of the day? What do you typically do on a weekday at about 8 a.m.? Or what do I do? Obviously, you're not at my house, but think about, what did regular people do at about 8 a.m.? Exactly. So if we go to work, what does that mean? We're like opening up a garage door. We're opening up a door to the house. What's going to happen? Perhaps that radon that's been settling in all night in a closed up house now has a way to escape. And so that's what's most likely happened. You can see something similar. Let's see here. Look at 6 p.m. when the lowest value is there. And what happens about 5, 6 p.m.? Well, you might be getting home from work. And so that's, unfortunately, we don't have that much data here to really attack this seasonal aspect. And so this is something that can happen when you have data, time series data, is that, here we have a few days worth of data. And so essentially, if I have I think at most I have 4 days worth of stuff, it's really, really hard to estimate that seasonal effect if you only have basically 4 time periods across the season where something like this is going to happen. So this is something to always take into account, that whenever you have time series data and it's seasonal, you need to have enough data so that you can actually try to get a good sense of what that season is actually doing. Think of it just from let's say if you have non-seasonal data and you're doing some of these SARIMA models. If someone only told you only had 4 observations, do you think you could really find a good model for it? No. You need more. And so to get it to seasonal, it's the same aspect. But it just, I don't know what the right word is. It just amplifies itself in terms of how big of a sample size you're going to need when you have the seasonal part. And here's my little public service announcement, or not public service announcement, but just in case the radon thing I told you is the second leading cause of lung cancer in the United States. And here we see the United States broken up, I believe, by county. And the red corresponds to areas of the United States where the radon is the highest. In fact, it says average indoor radon levels may be greater than that 4 cutoff that we've seen before. And we can see that indeed, if you see where my mouse is, Lincoln's in the red area. And so this is what happened to my house is common in other parts of the country too. But if you really wanted to investigate this further, and I haven't done too much in terms of how time series analysis has been used with respect to radon. Here are 2 particular papers, and I know you don't have this particular file, but you can always look at the corresponding video, get the web address from there. And so in particular, this particular paper here, let me show you what it looks like. So it gives us some information about, they're trying to do something about a radon index, but the key thing that I wanted to point out here is that figure 2. Figure 2 is autocorrelation of the radon time series. So they're actually using ACF plots to better understand how radon occurs with respect to a lag. So that's kind of interesting. Now, their ACF plot looks a little bit different from ours, but basically they just, where we have, let's say, autocorrelation drawn out from a horizontal line at 0, and we have vertical bars going up or down. They just simply, where that vertical bar would go up top, they just draw a line to the next vertical bar and then the next vertical bar and so on. Sometimes you'll see people do ACF plots like that, which is different from what we've done, and that's essentially what they're doing here. They also have some data on the left that actually shows radon observed over time. So a simple application of what we're doing here. Let's see here. Here's something that is of, unfortunately, current interest. If you've been following the news media, you know that in Taiwan they recently had an earthquake. And so here's actually a book chapter that talked about radon time series data for earthquake precursory studies in Taiwan. So what they were trying to do was investigate, could we use, let's say, changes in the presence of radon to help predict earthquakes? Well, radon exists in the ground. So that, at least intuitively, makes some sense. And so that's what this book chapter is talking about. Okay. So project number 3. So all of you should have received project number 3 back since we last met. And, again, these grades were very good. Average score is 33.2 out of 34. And I was looking through the project to see if there was any comments I wanted to make about it. And, well, when you have grades this good, it's hard to make a comment. So I don't. But I would recommend that you take a look at how I approached number 1G. That was that example dealing with, let's say, if you're being interviewed by the news media and you had to give some comment about forecasting earthquakes. There's multiple ways to handle this, but I have faced similar situations like this in the past, and so I just used that background to give what I thought would be an appropriate response. Are there any questions regarding project number 3? Okay. Remember how this earthquake data was motivated by how hurricane predictions are done. And I, just from the listening to the news media this week, maybe you saw this as well, the first hurricane predictions came out for the Atlantic Ocean this year. And it's going to be a record year in terms of the number of hurricanes that are being predicted. Here, for example, is one particular thing that was in the news media. And they predict 23 named storms in all. What this means could be like a tropical storm, not necessarily a hurricane. Maybe a tropical depression. I don't remember if they named tropical depressions or not. And so they're predicting 23. And this got me interested in learning more about how they're actually doing this. Because after all, they have a forecaster who's doing this. So maybe this individual is using some kind of time series models in the end. At least through my, let's say, half hour that I was taking a closer look at it, I couldn't figure out exactly what they were doing. But, if time series analysis is of interest, and if maybe this particular application is of interest, this is a case where you, since you're in grad school, you came to grad school to really learn about this kind of stuff, to get into the details. This is a place where you could do some explorations on your own. And just to help you get started off, if you're interested, I guess it's at Colorado State University where they are the ones who are doing these, taking the lead in these forecasts and stuff. And I was searching around their website trying to figure out more, like exactly what are they doing. And there's a paper on their website that explains it a little bit. They say, we use a statistical dynamical hybrid model based upon 25 to 40 years worth of evidence or past data to make their predictions. That's about as far as I could get in terms of figuring out what they were doing. They do mention, they use Poisson and Weibull probability distributions in their predictions, but they didn't say how. I have to admit, I was kind of disappointed. So anyway, so it's something interesting. If you're curious, that's a starting place to look at this further. Okay, let's get to the main things for today. So project number 4. Hopefully all of you have taken a look at project number 4. I've kind of told you a little bit about what to expect on it. The project, first of all, is due Thursday, April 18th at 8 p.m. And basically, what you're doing with the earthquake data, find the best model. And, we've already done a lot of stuff with the earthquake data. So rather than have you repeat some of the stuff that we've done, you can skip steps 1 and 2 the model building process when you're investigating this earthquake data. In the last project, or in previous projects, we thought in ARIMA 101 and ARIMA 100 were candidate models to consider. I want you to also consider an ARIMA 001 model to see what happens. Now, starting with those 3 models, go through steps 3 through 6 of the model building process. So step 3, estimate the models. Step 4, do these diagnostic methods. Okay? See where this takes you. In the end, choose one overall model. With this overall model, let's predict or let's forecast 1, 2, 3 years into the future. Let's do some nice plots with this. Make sure you fully state your final model, all that good stuff. I think one will be straightforward. Oh, I shouldn't say I think. I've already done it. It is straightforward. Number 2, though, is now the Shiny app data. We haven't seen that data since project number 1. Just to review, this is what the Shiny app data looks like when it's plotted. So we have 1 year's worth of number of visits to my Shiny app website. And what we like to be able to do is find the best model for this data. We have daily observations. And so we have a seasonal aspect here. What will be the season then? What's the season length? 7 days. Okay. And think about what that means. These are typically the people who were using my app were people who work in laboratories. Do they work Saturdays and Sundays typically? Typically not. I mean, during the pandemic, things got really, really busy for these people. And I know some did work on the weekends. But, typically in a normal situation, these laboratories who were doing the testing for SARS-CoV-2, they were not working weekends. So as you might imagine then, probably the number of visits to my website will go down on the weekends compared to what it would be on a weekday. And so there's my seasonal aspect. Every week we're going to see something like that happen, that pattern. Okay. Let me actually make this a little bit bigger. Okay, so what I want you to do is perform all 6 steps of the model building process. Nicely label everything. It's good. You got to really make sure you organize everything nicely. That's just to make it look professional, and also it makes it much easier for me to grade too. Now, to help you out, here are some comments. The stuff in red's different from, or it's not in the actual thing that's on my website. For all the plots of the actual time series itself, it's okay to use t on the x-axis rather than date. It just is going to make it easier for you. Eventually, let's say if you were actually trying to do this you're on a job, you're trying to do a report, and you might want to maybe, let's say, provide some plots where you have the forecasts on it. At that point, in the real world, you would put actual dates just so that we can put it into context about what's going on rather than having t on the x-axis. But just for this project, let's just make it simple. Just use t. First differences with respect to lag 1 should not be used for this data. Maybe you might need differences with respect to the season. You'll have to make that judgment based upon the methods that we've talked about in the past about whether or not that's needed. But at least with respect to the non-seasonal aspect, do not use differencing. For the forecast part, state the forecasts with the corresponding confidence intervals. Let's just do 1 week, a 1 week forecast. Make sure you include appropriate plots. Make sure for the final model that you choose, state the estimated model by typing it out with the actual estimated parameters. In my notes in my videos, I emphasize that, but I'm just emphasizing here as well. I want to see the actual model stated. So I want to see the phi hat 1, for example, if there's a phi hat 1 in it. Now, one thing that made things complicated when I was doing this myself, I had normality problems that I needed to solve. And I had to use a transformation to solve the problem. We've talked about a few different transformations, like the log transformation. But maybe the log doesn't work here. And then lastly, odd things happened when I found the confidence intervals for the future values. In terms of these confidence intervals were a little weird. I don't want to go into details. That would just spoil the fun. But the reason why I tell you this is don't be alarmed if you see something like, oh, I've never seen that happen before, if that happens. Okay? Of course, you're welcome if you find it confusing what at least the model that I chose in the end. If you end up choosing a similar model, this will happen to you. And if you find it confusing and you want to talk to me about it, you're welcome to talk to me about it. And we'll discuss why that's happening. But I want you to, if you go down the same path as I did, I want you to encounter it. In the end, I will have to admit that I was not 100% satisfied with my final model here. Okay? Maybe you can do better than what I did. But I was not 100% satisfied. So that's project number 4. Are there any questions? Okay, so let's do one more thing today. And that is, I believe it was last time, or maybe it was the time before. Yeah, I think it was last time. And we were talking about the AIC and how I would almost put another problem on the project dealing with the AIC, where one would actually investigate, does the AIC actually work? Does it actually pick the correct model, just itself? And in fact, I think we saw an example in the notes where it actually did pick the wrong model. And so how could we explore this further? And so what we're going to do is a little bit of an exercise here, where we're going to approach this from a research perspective. Many, if not most of you, will do some kind of research aspect while you're here at UNL. How would we investigate this from a research point of view? And so the stuff that I'm going to be doing is in this particular program, aicinvestigation.r. I will post that after class. And who knows, maybe there could be a question on test number 2 about this investigation. Okay. So, we've seen situations where, we state a particular model. We can simulate data from that model. And since we know what the true model is, this helps us to investigate, did the statistical methods work? And essentially, that's how we're going to approach this particular problem here. Let's say that I have an ARIMA 202 model from which I'm going to simulate my data from. Notice I've stated my phi 1, my phi 2. There's theta 1, there's theta 2. And let's do a sufficiently large sample size, let's say 200. I'm going to set a seed so I can reproduce my result. And here's my simulated data. Okay. I could go ahead and estimate a model to this data. Let's actually estimate the correct model just to see what happens. And I could get then the corresponding AIC. Now, how did I know that the AIC was located in this part of this return component? Well, this is where, again, using names function helps. And I see names mod.fit. I could take a look at, there's my AIC. If there was any doubt that that was the actual AIC that we wanted, we could look up in the help for this ARIMA function and see in the help, it will tell you what components are returned in this list. Okay. So what I'm going to do, so what this shows is that we can simulate data, we can estimate a model, we can get the AIC out. Now, what we now need to do for this, let's say this research problem, is that we need to do this process for also other potential models. So I need to estimate it maybe for an ARIMA 101 model, get the AIC, store it somehow. Maybe do an ARIMA 303 model, get the AIC, store it. Do that for this simulated data set, but do this then for a large number of simulated data sets, because we know one simulated data set is not going to necessarily give us the information that we want. Maybe we got lucky one time when we got the correct model. But maybe we need to simulate this over 1,000 data sets. And for each 1,000 data sets, look at a whole bunch of ARIMA models, get the AIC outs, look to see which is the best model amongst all these for each data set, and then compare it to what the true model is. I didn't necessarily explain that very well. Let me start that again. So what we're going to do is we're going to simulate a data set, estimate a bunch of models to it. For each model, we're going to get an AIC out. We know that the model that has the lowest AIC is the best, so we find that model. We do that for one simulated data set, and then we repeat the process for another simulated data set. We repeat the process for another simulated data set on top of that. We do this a large number of times, and we look at overall, how often did I get the correct model? This will tell me, did the AIC do its job correctly? Okay, so that's what we're going to do. So it's kind of involved. Now, the number one thing that I will see students get wrong when they try to approach a problem like this is that they will immediately try to do exactly what I said and program it in and try to get it right. Okay? The problem, though, is that there's a number of essentially steps that need to be done. And if you start at trying to get to the last step first, it will often lead you not to get to that last step. And so what you need to do, and this is a very, very important thing whenever you have a research problem like this, is break this problem up into simpler parts. Solve the simpler part first, then go to a little bit more complicated part, then go to a little bit more complicated part after that, until you get to the grand scheme of what you want to get done. And so that's what I've tried to do, or to illustrate with my program here. So as you will see here, I broke this up into steps. So step 1, we actually just did. We showed how we could simulate a data set, estimate a model to the data set, get the AIC out. Now step number 2 is, I want to be able to simulate a data set again, but now fit a bunch of different models to it and get the AIC out every single time. So let's look at how we can do that. So here's my data simulation once again. And then what I'm going to do is look at a bunch of different models. And basically I want to look at, let's say, P equals 0, 1, 2, and as high as I want to go. How about we just cap it at 3? So P at most can be 3, but I'm going to look at all possible models that correspond to 0, 1, 2, and 3 for P. Similarly, I'm going to do the same thing for Q, 0, 1, 2, and 3. So how many total different models am I going to be looking at? I can go 0 to 3 for P, 0 to 3 for Q. There are 4 possibilities for P, 4 possibilities for Q. So that means 16 different models. There's one model that's right, and that's the SARIMA 202. So I'm going to create some objects that allow me to put what my maximum P, maximum Q are. So you can think of, well, why did I do it like this? Well, let's say if I wanted to change my problem up and use some other kind of maximum. Maybe I wanted to go up to 5 or something like that. Now, for each of the models I'm going to investigate, all 16 models, I want to be able to save my AIC that I get from them. And so I'm going to create a matrix called save.aic that's going to be, first of all, initialized with nothing in there. That's what the NA basically means. Where the number of rows in the matrix is going to correspond to the number of models I'm going to fit. So it's going to be 16 rows. The number of columns is going to be 3. And the reason being is because the way I'm going to structure this is that each row is going to correspond to a model. Then I'm going to have a column corresponding to P, tells me what the P was. A column corresponding to Q, tells me the Q. And then a column corresponding to the AIC. I'm going to put that into an object called save.aic. And so this is what we get. Now, I like to be able to make this information that I'm going to store in there in terms of to label. I like to be able to label the columns to make them more descriptive, just to help me out. And so what I can do is use the call names function, which stands for column names. So the column names of save.aic is going to be equal to the P, the Q, and the AIC. So let me go ahead and do that, and then we can now look at that matrix. Now, just a little bit of a side note of using R. Usually, we only have functions being used on the right side of that assignment operator, that's less than dash, or for those of you who really like the equal sign. Typically we only put functions on the right side. This is one of the very few times where you can actually put it on the left side, as what you see here. Kind of just a little interesting oddity of R. Okay. Next, I need some way to nicely generate all the possible values of P and Q I'm looking at. So I like to be able to look at P equals 0, Q equals 0. Then P equals 0, Q equals 1. Then P equals 0, Q equals 2, and so on. So as you might expect, a for loop is going to be helpful. In fact, 2 for loops. So I'm going to say for P in 0 to 3, or max.p. Notice the curly bracket there to say what's inside my for loop. Then another for loop, Q in 0 to 3. Again, look where my curly brackets are. And then inside of it, I'm going to simply estimate the model for that particular value of P, for that very particular value of Q. Next, I'm going to extract out, just like what we saw before in step 1, I'm going to extract out the AIC. But the way I'm going to extract it is, or I shouldn't say the way I'm going to extract it, is that I'm going to combine this together with P and Q into a vector, and then put that into a particular row of my save.aic matrix. The row is called counter. Simply, you've probably encountered this before with for loops or other kinds of looping structures, is that I'm going to initialize something called counter at 1, and then every time through the loop, I'm going to simply increment it up by 1. So that goes into that particular row of that matrix. So the first time through my loop, P0, Q is equal to 0. I'm going to estimate a very non-interesting model with P equals 0, Q equals 0. Extract out the AIC. I'm going to put a 0 here, a 0 here, and it's going to go into row 1 of save.aic. And notice how I'm making that assignment there. So let's go ahead and run that and then print the results. And there is all my AICs corresponding to the models. So here's a question for you that sometimes students are unsure about. You know, a diagnostic tool that we often use whenever we have a for loop is that we actually print off the contents of what's going on in the for loop at each iteration. How could I do that here in R? Let's say I wanted to see, you know, this that I have highlighted. I want to see that at each step as it's being evaluated. How could I do that? You could do print. And there you go. Okay. Now, what would happen, though, if I just did this? Because normally, if I were just to put that at a command prompt, hit enter, I would have results printed back to me. Well, let's see what happens if I do that here. It doesn't happen. So this is something to understand about R, that if you do this inside of a for loop structure, that will not be printed. And in fact, the same thing occurs if you have this inside of a function itself. That if you were just to type, you know, what you want to see come back to the come back and printed, you know, what you would normally do at a command prompt, that will not be printed if you put that inside of a function that you've written. Instead, you always have to use print, or there's another function that you can use. Does anyone know what that function is? Starts with a C. Then there's an A. Thank you. Cat. This can be useful as follows. Let's say if you wanted to include some kind of label, like each iteration. I mean, this is just kind of made up. I could do that instead. And actually I'm going to do one other thing that's going to make this look a lot nicer. So inside a cat, you can put the stuff that you want printed. You can separate stuff by commas. So sometimes you want to actually put a text string that you've created. Sometimes you want to have the actual numerical values, like P and Q printed. So you separate everything by commas. And if I also use /n, this is then getting into basically Linux, or this is the origin of it. When you use a slash like that, that means it's what's called an escape character. And /n, for some reason, I don't know why, means go down to the next line when you're done. And so we can see what happens with it and without it. Okay, so that's with it. And if I do not include it, we have a mess. So that's why I use that /n. That /n is actually discussed in my introduction to R set of notes as well. I'll leave this in this program for those of you who are interested. Okay. So, are there any questions? Are you comfortable with how this for loop was used, how I insert stuff into the matrix to save it? Any questions about it? It's a very important thing. Okay. So now I have all these AICs for one simulated data set. And so what I need to do next is figure out what's the minimum AIC. So, I could simply look throughout here and do it, but we would like an automated way to do it because we'd like to be able to, in the end, do this for many simulated data sets. And so, we can use the function min. So if you remember the structure of save.aic, the third column was all the AICs. And so if I did min, and I just say I want to just use that third column, I get my minimum to be 553. So that's a valid way to do it. One way to do this in a more, I guess maybe a better programming way, more descriptive, is that I can extract out just that third column by just giving the name of the third column, which was AIC. I could do that as well. And of course, if I run this, I get exactly the same thing. Okay, so now I know what the minimum is. But what we really want to know is what was P, what was Q. This tells me what my model is. This tells me, did AIC work? Did it pick the correct model? So I need to figure out which row is 553.5881. I need to do this in an automated manner. So what I can do is this. I can look again at everything that's in that third column and check, is it equal to the minimum value? So if I execute this code here, what's going to happen? What's going to be returned to me? Yep, trues and falses. Okay, where the true is the corresponding element where it matched. And so if I want to now figure out what is P, what is Q in an automated manner, what I can do is take all those trues and falses that we just found, put them in the row designation of my matrix. And what's going to happen then is I get the corresponding row come back to me. Only the true row comes back to me. So notice that this is equivalent as false. So let's see, 1, 2, 3, 4, 5, 6, 7. The seventh row is what I want. So if I did save.aic, left square bracket, 7, comma, right square bracket, I get that row out. But R also takes these trues and falses to mean that true is that actual corresponding row that you want. And so that's how I extracted it. Okay. So, step 2 of this process, we figured out how we could estimate a whole bunch of different models. and then find what was the actual model that had the smallest AIC. Did the AIC work for this data set then? No. Remember, our true model is ARIMA 202. What was picked? 102. Now, we have all this code to do this. How about we put this code now into a function so that we can apply this whenever we want to, multiple times, and we don't have to type out all that exact same code every single time. So that's what I did next. I'm going to create a function called find.aic.smallest. In this function, I'm going to pass in information about, well, what's the model? What is the true model? I should put probably true model there. But what is the model that I'm simulating the data from? What is my sample size that I want? And then I have some other arguments that I have some defaults for, like the standard deviation, the max.p, the max.q that we saw before. And basically, all the code that we saw above, I copied and pasted it into this function here. I left out some stuff that was allow us to eventually get to where we needed to be, like how do we find that corresponding model? And so note that this function has a very last line that is the model that had the lowest AIC. That's going to be what's returned to me. So let's try to actually run this function now. I'm going to use the exact same seed as I did before when I simulated the data. Find.aic.smallest. Here's how I specify my model before. Remember how we put it into a list. That's just a standard way of using arima.sim. But I'm just going to pass that into my function. I'm going to use a sample size of 200 as before. And so if I run this, all this code, I should get exactly the same as what we did before. So again, that's step 3 of this process. And just for emphasis, started something simple. I made it a little bit more complicated. I made it a little bit more complicated so that I can get to where I want to actually be. So what we have here is a function that it can simulate one data set, fit a whole bunch of different models, find the model that has the smallest AIC. What I'd like to be able to do next now is repeat this process many, many times. Let's say 1,000 times, and see how often AIC picks the correct model. So to do that, then we go to step 4. And this is essentially the last step. Because of time restrictions here, we're just going to simulate 10 different data sets. And so I create an object called sim.num, for the lack of a better name, that number of simulated data sets. I do this on purpose like this because it allows me to easily extend this to 1,000 in the end, if I wanted to. Next, I need to create another one of these save matrices. What this is going to have is that for each simulated data set, what was the best model? So I initialize its contents with NAs. The number of rows, each row is going to correspond to one simulated data set, the model that's chosen. So that means if I'm simulating 10 data sets, I'm going to have 10 rows. I'm going to have 3 columns again, which are going to correspond to the P, the Q that were chosen, and then the AIC. So let's go ahead and just run that, and I can show you what that looks like. There we go. And so I'm going to set a seed so I can reproduce my results. I use one for loop. I in 1 to sim.num, 1 to 10, do the following. Put into row I of sim.res the results simply from find.aic.smallest. And just so that we can see the progress, how about we print the I? This is often, whenever you have, and you probably encountered this elsewhere, whenever you have something that can run some time, it's good to know how far along are you in the process? How much longer do I need to wait? So if I print the I, the iteration number essentially, this allows me to see it. And then in the end, I'm going to print off the results. So let's go ahead and run all this. And this is what we get. So for the first simulated data set, an ARIMA 1-2 model was chosen. There's the smallest AIC. In fact, this is exactly the same data set as we had before because we use the same C number. But now for the second data set, an ARIMA 1-3 model was chosen. There's my AIC. Ooh, data set 3, ARIMA 3-0 model is chosen, and so on. We have some warning messages here. Just ignore those for now. Okay. So now, how often then was an ARIMA 202 model chosen? Well, let's figure out how we can do this in an automated way for us to check. So save.res, I have a column called P, which corresponds to the actual P that was chosen. I want to check how often was it equal to 2. That will be the correct answer. And so we get trues and falses for that. But I also want to do the same thing with my Q column as well. And I would like to do this jointly for P and Q simultaneously. How often do I get that right? And this is where I can use then an R, the ampersand, which means and. And so whenever I have a true on the left and a true on the right, I will get a true together. If I had a true here and a false there, I will get a false because the model's not right. So let's do that. And you can see there's only 2 trues. What's the proportion? Well, 2 out of 10. Or how about we just simply say sum all those trues and falses. R converts the trues to 1s, the falses to 0s. Divide by the number of simulated data sets. And there's my 0.2. So only 20% of the time for these 10 simulated data sets did the model come out right. You might be thinking, oh, geez, you only did it 10, Chris. You were talking about 1,000. We could do 1,000, but I actually, before class, I did 100. And let's see here. And so if you use the exact same code, put 100 here instead. It will take a little bit more time, and I'm not going to take the time to do that, but we can do the same process. Oops. And it just so happens it's still 20%. So out of 100 data sets, only 20% of the time did AIC get it right. I have to admit I was a little surprised. So now we have some research questions then that would be of interest here, because the statistical method is not performing as we would expect. So first of all, what model is chosen the most? And you do a little bit of investigation and find out it's actually the ARIMA 102 model. 49% of the time is chosen. Any thoughts about why that would have happened? Why 102? Why is it missing P? Based upon something that's on the screen right now, you might be able to figure it out. I don't think that's the reason, but it does have something to do with 0.2. It's low. It's close to 0. That's why. It's going to be harder to show that it's, let's say, non-zero because it's kind of close to 0. That's why. That's why it's missing that it's missing that phi 2. So that's kind of interesting. Now, if I were to use larger sample sizes, what do you think would happen? Well, it's probably going to get that second 2 more often. You can try that on your own. And so that's, again, something that you would do in research. Okay, now let's try a larger sample size, see what happens. Is then the procedure performing like I would expect? So what we've done here is we've set up a way where we could investigate this problem further. But if one was, let's say, doing this for a real life research problem, you wouldn't just stop there. You wouldn't do further investigations. You could look at other values of P, other values of Q, other values for your AR parameters, other values for your MA parameters. See what happens. See when it's working and when it's not. Then you could come up with some, let's say, general recommendations for practice. It's always important then to look at, well, when does the AIC get it wrong? Okay, so one thing that I skipped over. So when we ran the code, we got some warning messages. And unfortunately, whenever you're doing some kind of Monte Carlo simulation study, which this is, and you're trying to fit a model, often what happens is you get some of these weird situations where the model fitting doesn't work. And then what should you do? Go investigate, why did it occur? When putting this together, I ran out of time. I didn't investigate that. It would be definitely of interest to figure out, why are we getting this non-convergence? I guess where I got stuck, because I saw this and I spent a little bit of time trying to investigate, is, at least immediately when I was doing this, I could not figure out, I shouldn't say immediately, I took about at least 10 minutes, maybe 15 minutes, trying to figure out, how can I extract information about that would tell me, did ARIMA converge, or did the ARIMA function lead to convergence or not? I want an automated way to do that. And so that I can take that into account here, and there's a number of different approaches that one could follow. For your investigation here, what you might do is throw out the data sets that did not have convergence, and then just look at the remaining data sets. Look at that proportion. How often did AIC get it right? Still, if you're writing, let's say, a paper on this, you would need to report, I had non-convergence this many times. And if it's sufficiently large, then you're going to need to figure out why that occurred. Unfortunately, I ran out of time, and I didn't have a full, I wasn't able to fully investigate this part. So, any questions or any discussion regarding this? Okay. So let's just end with, well, what's next in our class? So again, I'll be available for questions after class. You do have a quiz that's due at 8 p.m. today. Thursday, I'll have my usual office hours. And also at 9:30, we'll have our help class. It might be a great time to get together again with your group to get going on this project. So next Tuesday, I will have my normal office hours. We'll have we'll have our normal class. 2 subsections. The first one deals with an example with a SARIMA model. This is, we've talked about this data set once before. It's my Oklahoma State University enrollment data that actually I encountered when I was a professor at Oklahoma State University. And it had some real life consequences out there regarding the data and the background of the problem. Then finally, we get done with section 3 with that. Now we're going to go into section 4. Section 4 are specific additional topics for our course. So section 3 kind of built upon each subsection to some extent. Section 4 does not necessarily do that. And the first special topic or additional topic that we're going to investigate are what are called RFEMA models. So we have an F there in the middle of ARIMA. The F stands for fractional. These models are used when you have what are called a long memory time series, where this autocorrelation that you have across the lags just seems like it just never goes away. It just persists, lag 50, lag 100. But it's not what you would expect if you had non-stationarity in the mean, where you have very large autocorrelations. If you imagine my ACF plot that's right in front of my eyes right now, you have large autocorrelations. That would be non-stationarity in the mean. Instead, you have autocorrelation that persists over many, many lags, but it's not necessarily large. How can you deal with it? And so that's what these RFEMA models look at. And in the end, instead of, let's say, using d equal 1, maybe you might use d equal 0.3. That's where the fractional part of that name comes in. So this corresponds to sections 3.9 and 5.1 of the Shumway and Stouffer book. Also, next time we'll address any questions that might be regarding project number 4. I do strongly recommend that you get going on this definitely before Tuesday, primarily because of that Shiny app data set. There will be a question. There will be another Canvas quiz. Then looking further ahead, project number 4 is due Thursday, April 18th. And then this test is coming up quickly. April 25th at 9 a.m. I actually wrote the test yesterday. So at least the first draft of it. Are there any last questions? Okay, that's all for today then.